So now that we've seen how the heap bins work during normal operation and how chunks can flow between the different bins based upon what is occurring, let's take a look at how we can apply those concepts to control the heap and start getting it to do what we want. Now, before going any further, it's worth emphasizing that heap exploits are heavily dependent on the libc version. For this module, all of the challenges should be working with libc version 2.35, which is the latest version of libc that is used on Ubuntu 22.04 LTS. I do believe libc version 2.36 is out. However, I do not intend on using it for these challenges. If for whatever reason any of the challenges use a different version of libc than version 2.35, the challenge will explicitly state it. Now, the reason that the libc version matters is different versions of libc will have different validation checks or verification checks. And so the requirement as far as what you can do and what you can change is going to be different for every version of libc. A good example of this that we've seen is safe linking. Safe linking is present on modern libc in tcache and fastbin. However, if we were to go back a couple versions of libc, there is no safe linking on tcache or fastbin. And if we were to go a few versions back from there, the tcache itself doesn't exist, but we would still encounter fastbin. And so when you're looking online for heap exploitation, it's very important to be aware of how old is this exploit. What version of libc was this written against? Because there are fastbin exploits that used to work on libc that didn't have tcache. Just the introduction of tcache changed the way that we interact with fastbin. Now, sometimes features aren't added like tcache, but actually removed. A good example of this is the malloc hook symbol, which was meant for debugging purposes. It was a symbol where you could write an address, and whatever that address was would get called when malloc was called. Now, this was such a common vector for exploitation that it was actually removed from libc entirely. And so if you find a heap exploit online that relies on malloc hook, that doesn't exist anymore. Now, it would take several hours to go through all of the specific named heap exploits that exist and work in libc 2.35. And all of them are very nuanced. There's a very specific setup that is occurring to create the situation inside of the heap where the exploit can occur. Rather than do that, I'm going to discuss some of the core concepts that are used in these exploits so that when you look at them, you can reason about what is occurring and what you need to do to create the same scenario and replicate an exploit that you see. Now, many of the concepts that are used in these more complicated heap exploits are things that we've already seen because we've done them in earlier heap modules with tcache. Things like creating a double free. You may need to create a double free to even begin the exploitation process for a more complicated heap exploit, or having a use after free. We've seen use after free. Many of the named heap exploits require a use after free in order to pull them off. So when you look at these named heap exploits and you see that they need a use after free, you should be thinking, how can I create a use after free primitive in the challenge to replicate that exploitation technique? If I can't create a use after free, then that technique simply won't apply. Two other things that we've seen that also exist in more complicated heap exploitation is corrupting heap metadata. We've seen this where we overflow from one allocation into the next and corrupt tcache metadata. The same thing exists on the heap, except the metadata is slightly different. Because now we have those forward and backward pointers. It's now a doubly linked list. We have different verification steps. But the same principle still exists. We can corrupt memory and corrupt that metadata to make the heap misbehave or act in an unintended manner. Lastly, in the module, we saw overlapping allocations on the tcache. overlapping allocations still exist with the heap. Now, it's going to be a little bit more difficult to create an overlapping allocation because the metadata is more complex. But the overlapping allocation primitive can still be created. Now, there are exploitation techniques that exist on the heap that didn't exist with tcache. And one of those things is taking advantage of consolidation, because tcache doesn't consolidate. So what can we do with consolidation? Well, there's a couple things to keep in mind. First, remember that chunks that do not go to tcache or fastbin go to the unsorted bin. They're all kind of given that extra life to see if the chunk can come back from the unsorted bin. Well, we can control what happens at the unsorted bin. A correctly sized, like a large malloc, can clear the fast bin and the unsorted bin and cause consolidation. Similarly, maybe there is an allocation that I do not want to be consolidated, but I still want to clear out the bin. Well, we can do that by carefully crafting the heap such that we have a guard allocation. And this guard allocation solely exists to prevent consolidation from occurring to another chunk. Let's take a look at how that works. All right, so what I have here is a kind of toy program very similar to what we've seen with some of the heap challenges in the earlier modules. A lot of heap challenges follow this type of loop format where you can malloc, free, update, read, write, that type of thing. Now, for our purposes, all I need is malloc and free. So my first claim was that with a correctly sized large malloc, we can clear the fast bin or the unsorted bin and cause consolidation. So let's look at my code for that. So I'm going to malloc 9 times in total. I'm going to malloc 7 times because I intend to free them into the tcache. I'm going to free an additional 2 because I intend these to go to the fast bin. Note that the size of my allocation is small. So this is an allocation that is eligible to go to fast bin. I'm going to print the PID and then go interactive so that we can take a look at it in GDB and see what's going on. All right, let's attach GDB. So the first thing I want to look at is the bins. And we see that what I intended to occur is what occurred. We have 7 chunks in the tcache, and we have 2 chunks here in the fast bin. We'll note that one of them is 27A0, and the other one is 27C0. Now, this is the order of them in this singly linked list of fastbin. There's another command that I can use to look at the physical location of the chunks and reason about where they are in memory. And that would be heap chunks. And we see here that there is a chunk 27A0, and then immediately after that is 27C0. So these 2 chunks are right next to each other in physical memory. If I didn't print this out, I could still reason that that is the case because 827A0 plus hex 20 is 827C0. It's also worth noting that we have A0, we have C0, and then we have the wilderness. This last chunk here is very large, but this represents all of the unallocated data that exists currently in the heap. So what's going to occur when I malloc something large? Well, if I malloc something large, it is not going to be satisfied by the tcache. It's not going to be satisfied by fastbin. It's not going to look in the small bin because I'm mallocing something large. And so that means that we're going to flush the fast bins. When we flush the fast bins, these chunks will become eligible for consolidation. Now, remember that consolidation is determined by this previous in use bit. And even though the previous of 27C0, which is 27A0, even though this one should be marked as previous not in use, it is marked as previous in use. This is because it's in the fast bins. So whenever we flush the fast bins, 27C0, the previous in use bit is going to be cleared, which then makes it eligible for consolidation. And when that gets consolidated, it will merge with 27A0 and it will consolidate backwards. But it can also consolidate forward into the wilderness. And so what we'll see is all of these chunks here will suddenly become 1. So let's malloc something large and then take a look at heap chunks. And what happened? Well, we saw I claimed that all of these would merge together into 1. And they did. And they did that before we returned an answer to this malloc. So we merged it all together into one giant chunk, starting at 27A0. Then we had to satisfy that malloc. And so we had this giant chunk and we broke off 2,000 bytes and returned it. But where did those 2,000 bytes begin? They began at 827A0. And so we see the address that was returned by this malloc is the same as the address that was returned by this malloc, despite the sizes being drastically different. And so we can cause consolidation to occur. And you can do a similar thing with the unsorted bin. You would malloc something that is larger than the values in the unsorted bin, and it would sort the unsorted bin. Now you can get a little bit creative here with the unsorted bin, because if you strategically place increasing values into the unsorted bin, like let's say we put, I don't know, let's do hex 2000, then hex 3000, then hex 4000 into the unsorted bin. And then I put in a malloc request for hex 3000. What's going to happen? Well, it's going to look at the hex 2000 and say, this is unsatisfactory. I can't make 3000 out of 2000. And so it would sort the 2000 byte chunk. Then it would grab and look at the 3000 byte chunk and say, can I make a 3000 byte chunk out of 3000 bytes? Well, the answer is yes. This is exactly what I need. And so it would stop sorting and return the 3000 byte chunk. The 4000 byte chunk doesn't even get looked at. It's still sitting in the unsorted bin. And so with the unsorted bin, you have a bit more control depending upon how much influence you have on the size of the chunks and the order of them in the unsorted bin, as far as flushing them out. Now, my second claim here is that conversely, you can choose to hold an allocation and prevent consolidation. Now, I could do this with the same number of chunks, but I feel that it's easier to understand if I slightly modify 1 in a clear manner. So the difference here between 1 and 2 is pretty small. We see here, I'm still mallocing 7 instances of size 8. I'm then going to malloc 2 that I intend to put into fastbin. And I'm going to malloc 1 more. And this 1 more is there to serve as like a consolidation guard, is what I'm going to call it. We're going to free the first 7 so that we fill the tcache. I'm then going to free index 7 I'm not going to free 8, and I am going to free 9. So let's run this and attach GDB to it. If we look at the bins, this looks very similar to what we've had in the prior example. I have 7 chunks freed into the tcache. I have 2 chunks here in fastbin. So what is different? What did this guard do? Well, let's look at heap chunks. Now, I have 2 entries in fastbin. I have 7A0 and I have 7E0. Well, here's 7A0 and here's 7E0. So my guard chunk was this one right here, ending in 7C0. So what will happen now, and it's sitting in between the 2 entries in fastbin. So what will happen now if I were to malloc something large? Well, we would still flush the fastbin. Like, that occurs no matter what. But when we flush the fastbin, we have to treat each one of these chunks differently. So 7E0, this chunk here, its previous in use bit will not change because the guard is still allocated. This is an in fastbin. So then when this chunk becomes available, it may consolidate forward into the wilderness. That could still occur, but it can't consolidate backwards. Now, what's going to happen with 7A0, which is this chunk right here that's in fastbin? Well, 7A0, its previous in-use bit, will it change? Well, the answer is no. What's behind it? 780. 780 is in use somewhere. So that's not going to change when we flush the fastbin. So what we'd expect to see is 7E0, which is this chunk right here, will consolidate forward. 7A0 is not eligible for consolidation. So where does this chunk go? Well, how big is it? This is a chunk of size hex 20. So if we had to sort this chunk and put it somewhere, it should end up in the small bins. So I am expecting to see 7A0 go to the small bins. Let's perform the large allocation and see how that influenced the heap. Well, looking at the bins, I do see that fast bins was flushed, which we knew was going to happen. The difference is 7A0 is now here in the small bins. And we see that it has a forward pointer and a backward pointer now, because now it is in the small bins, and so it's a part of a doubly linked list. Well, what happened to the other chunk that we were talking about? What was that one? 7E0. Well, I don't see 7E0 here. Why? Well, 7E0 consolidated forward with the wilderness and then was the location that a 2,000 byte chunk could be built from. And so it consolidated forward, and then that was the chunk from which a 2,000 byte chunk began. And so it began at that same spot. And then just for completeness sake here, we can look at heap chunks again. And what do we see here? Well, 7A0 is in the small bins. There is 7A0. But what changed here? Well, 7A0, when it moved from the fast bins to the small bins, it is clearly not in use. And so the chunk that immediately follows in physical memory, that immediately follows 7A0, which is 7C0, now has its previous in use bit cleared. And so this indicates that 7A0 is eligible for consolidation. However, it can't consolidate forward, right? Because of the guard. This is our guard allocation. And so it can't consolidate forward into that because the program still has it. And it can't consolidate backwards into 780 either. Why can't it go backwards into 780? Well, it can't go into 780 because 780 is currently held by tcache. And tcache performs that same kind of a trick where the previous in use bit is not cleared to prevent consolidation. And so right now, 7A0 can't consolidate backwards and it can't consolidate forwards, which is why it is now a small chunk in the small bin. And we are able to control that based upon our knowledge of how these mechanisms work. Now, in addition to working with consolidation or making consolidation work with us, we can also move chunks between the bins. Now, we already saw kind of flushing the fast bin out and how that works with consolidation. But we could also do something similar with the unsorted bin. In fact, we have more control with the unsorted bin because the unsorted bin is conditionally flushed and can be like partially moved through, depending upon the size of the chunks that are in it. Remember that if a malloc call is large enough to get to the unsorted bin can contain small chunks or large chunks. It can contain both. And the way that the unsorted bin is processed is a chunk is looked at. We grab the first chunk that's in the bin. If the chunk is too small for what we need, then we sort it and we place it in the correct bin. So we could place it in the small bins, we could place it in the large bins, but we put it where it needs to go. Then we grab the next chunk. If the chunk happens to be the exact size that we needed, that's great. We'll return that chunk to malloc right away. But if the chunk is too large, the chunk is larger than what we need, then what the allocator can do is the allocator will split that chunk right now while it's in the unsorted bin. It'll return the piece that is needed for malloc, and we'll leave the remainder in the unsorted bin. And so the unsorted bin is a location where chunks can also get split. And this means that we can create smaller chunks via the unsorted bin and then flush the unsorted bin to place those chunks where we want. You can also partially go through the unsorted bin. If the unsorted bin has chunks in increasing size, say it has a chunk of size 100, 1,000, and 10,000. If I request an 800 byte chunk, we would sort the 100 if we encounter that first. Then we would take the 1,000 byte chunk, split it off, and return an 800 byte chunk, an 816 byte chunk, if it was an 800 byte allocation. Well, we would put the remainder in the unsorted bin, and the super giant 10,000 byte chunk would be untouched. Because remember, we only process the unsorted bin until we find what we need. So it is possible to make malloc requests to partially go through the unsorted bin. And you can use that to your advantage. The last thing that I'll mention that I don't think was included in the discussion on the small bin was in certain scenarios, the small bin will take advantage of the fact that it is being accessed to load up the tcache. So if the tcache is empty, but there are small bins or small chunks in a small bin, and you're accessing that small bin right now, what the allocator will do is the allocator will reason that, since we are already accessing this small bin, let's take advantage of the fact that we're here to load up the tcache with up to 7 small chunks from that specific size bin that is being accessed. And we can take a look at how that works. All right, so this example here is very similar to the previous one, except instead of targeting the fast bin, I'm targeting the unsorted bin. And so I'm going to malloc 7 times with the intent of freeing them into the tcache. I'm going to malloc once, targeting the unsorted, and I'm going to malloc once more with a guard allocation to prevent forward consolidation. Now, how am I targeting the unsorted bin? Well, I'm choosing that by choosing a size that is large enough that it will not go into the fast bin. Remember, chunks up to 88 bytes and up to the fast bin. 128 is larger than 88, so when these get freed after the tcache, this should go to the unsorted bin. So that's getting freed then. I'm going to attach and take a look at the state of the program at that point. And what we see here is we have a chunk of size hex 90 in the unsorted bins. Well, why hex 90? Well, hex 90 is 144. 144 is 128 plus 16. Remember, there's 16 bytes for the chunk metadata. So what's going to happen if I continue running from this point? Well, what are we going to do? We're going to malloc 7 times, targeting the tcache. We're going to malloc once more with the intent of putting something in the unsorted bin. And I'm going to malloc a 9th time with a guard to prevent forward consolidation. Well, when this very first malloc occurs, that is going to go to the unsorted bin. And the unsorted bin has a 144 byte chunk here, which will be insufficient to satisfy this 256 byte malloc. So that means that we will sort this chunk. So this chunk should end up in the small bins. And that's going to happen on this very first malloc. Then we're going to do the rest of the mallocs and free 8 times. And that will place a 272 byte chunk in the unsorted. So let's move forward and see that. What we see now is the exact same thing because I didn't continue. Okay, what we see now is a larger chunk in the unsorted that is hex 110, which is 256. Oh, no, that's not right. There we go. 272, because it's 256 plus 16, which is what we would expect. And we saw that the 144 byte chunk was moved to the small bins. So we were able to flush this into the small bins while simultaneously placing something in the unsorted bin. Right? We didn't have to just malloc something very, very large and flush them all out. So I have another example. This is when we were putting something small in the unsorted and then mallocing something larger. What happens when we do the reverse? So this is just the later half of that, where we're going to put a 272 byte chunk into the unsorted and then go interactive. So let's run this and attach. And if we look here, we do have a 272 byte chunk in the unsorted. So what's going to happen if I malloc something smaller, like 64 bytes? Well, something interesting happens here. We still have something in the unsorted bin, but the unsorted bin chunk is now smaller. It is hex C0, but I didn't free anything. All I did was malloc. So what happened here? Well, we said when we're going through the unsorted bin, if the chunk is too small, we sort it. But if the chunk is too big, what do? Well, we can use this, except we don't want to return all of this extra space. And so we see this chunk began at 6E30. What was returned? 6E or 63E30. Let's find that over here again. 63E30. And so the allocation that was returned was cut out of that larger chunk right here. So then the thing that's in the unsorted bin is whatever was left after we cut out the allocation. So we picked up from the unsorted bin this chunk, who said, yeah, this is big enough. And then we just broke it in two and said, here's the piece that we need right now. We'll leave the remainder in the unsorted bin to deal with later. So what can I do from here? Well, if I malloc something very large, I can flush that remainder piece that was in the unsorted bin into the small bins. And so now, somehow, I've ended up with a chunk of size hex C0 in the small bins, even though the only thing that was freed into here was a chunk of size hex 110. And so you can take chunks that are in the unsorted bin, break them down, and then flush out pieces of the unsorted bin, and you can know what address will be there for that size. If I know the address of the original pointer up here, then I can know the address of the remaining piece that was broken off and flushed into the small bin. Now, the last thing that I claim we can do is small chunks can move into the tcache from the small bin opportunistically. Now, this is something that I didn't mention in the previous lecture about small bin. I'm not entirely sure. There's probably an exploit somewhere that uses this mechanism, but I'm not immediately aware of one. So what I'm going to do here is a little bit different. I'm going to malloc 7 times with the intention of freeing it into the tcache. I'm going to malloc twice more, targeting the small bins. How am I targeting small bins? Well, I'm going to fill the tcache. I'm going to make sure that these allocations are guarded so they don't consolidate. I'm going to free them into the unsorted bin. Then I'm going to force the unsorted bin to get sorted by mallocing something large. And that will cause these two chunks that were in the unsorted bin to get sorted and get placed into the small bin. Then I have an input. So let's take a look at a couple phases there to verify that is what's going on. 76079. So right now, I should have 2 chunks. So we are right here. I should have 2 chunks in the unsorted bin. And I do have 2 chunks in the unsorted bin. So now I'm going to malloc something large, which should flush them from the unsorted bin to the small bin. So let's do that. And now we see the unsorted bin is empty, and we have 2 chunks in the small bins. Now this is where it gets interesting. What I'm going to do is I'm going to clear the tcache. So I'm going to malloc 7 times to clear out the tcache. And then we're going to go interactive. So we see that the tcache does have 7 entries for the size that we are working with. And if we look at the bins right now, we've cleared out the tcache, and we still have 2 in the small bins, 2 chunks in the small bins for this size. Now what I want to do is I want to malloc just once. Now our intuition is, well, this is the correct size to come from the small bins, and so it should return the first chunk in the small bins. It should return 7BD0. Is that what happens? Well, it returned the other chunk. But it returned a chunk from the small bins. Right? And so that is what we would expect. But something interesting is going to happen here. If we take another look at the heap bins, the small bins are now empty. And the small bins are empty because that 7BD0 is now in the tcache. So what the heck happened here? Well, it turns out when there are more than one chunk in the small bins, and the tcache is not full, when we malloc, the allocator reasons about this and says, I have extra small chunks that could go into the tcache. As long as we're already working with this small bin list, let's load up the tcache. And so that's what happened here. We malloced once. We had 2 things in the small bin, right here and here. We malloced once. One of those small bin values was returned to us. It was 7AB0. And the other one, 7BD0, was placed inside the tcache for that size. So the allocator will preload tcache if it's already working with that size in the small bins. That's kind of interesting. There's a couple more things that are worth mentioning, although I'm not going to demo them, but they're definitely relevant for this module. The first is creating fake chunks. So we saw with tcache that we could override a next pointer and get the tcache heap to start returning values that it's not necessarily supposed to be able to do. Well, you can do something similar with the heap. However, it's not as simple as just overwriting a next pointer or performing safe linking modification, doing some XOR and writing a modified address to a next pointer. Because remember, the heap metadata has forward pointers and back pointers, and it has validation on those pointers. And it has validation on the size with the next chunk's previous size. And so there's these validation checks that constrain performing those type of modifications. However, if you have a region of memory that you can write and you have full control over it, you can carefully craft a region of memory by writing data that looks like heap metadata. So you'd have to write a previous size, possibly. You'd have to write a size. You'd have to write a forward pointer. You'd have to write a backward pointer. You may or may not need to write a forward and backward size pointer. Depending upon what part of the heap you're interacting with, there may be something that requires those pointers as well. But you could just write out memory so that it looks like heap metadata. Then, if you can corrupt existing heap chunks, you can get the heap to interpret your little region of memory as if it were the metadata of a heap chunk. So you can create fake chunks, but you have to be very skillful and particular in how you craft that memory region that you're going to be passing to the heap. Depending upon the specifics of what it is you're doing and what memory region you're working with, this can quickly result in a broken heap where tools like GDB and Jeff or pwn.debug will not necessarily be showing you correct information when you start printing out that heap debug information. Because it may try and follow the pointers in one direction, but because of the way that you've manipulated the heap, you have to follow the pointers in a different direction to reason about what's going on. And so you'll start needing to print out memory regions in GDB and looking at the raw bytes to reason about what is actually going on with the metadata. So this is something that you can do, but you can quickly end up with a broken heap and those corruption errors that I warned about in the first lecture. Now, similar to creating fake chunks, right? Creating a fake chunk is where you're trying to emulate the entire chunk metadata, right? And you're trying to do it reasonably faithfully. It is possible to simply take a memory region and try and craft it to just pass the validation steps. And you're just trying to pass the validation steps so that you can get one specific exploitation primitive. Like I just happen to be able to get an arbitrary read by creating a fake chunk that isn't a fully working fake chunk, but it's a fake chunk that works just enough so that I get an arbitrary pointer, an arbitrary read, an arbitrary write. I get some type of primitive that I can then work with. Just keep in mind that the more you're doing this breaking behavior of the heap, the closer you are to just utterly crashing. In the previous module where we were creating exploitation primitives, we were working with tcache. And tcache is great in the sense that if I break the tcache, I can always connect again and have a fresh thread, and I have a fresh tcache, right? Well, that isn't the case once you go past the tcache into the heap. The heap is the same heap for all threads in the process. So you don't have this quick reset button that you can just hit. And so this kind of brings us full circle. And so now we're back and looking at this unlinked chunk function that was back in the first lecture. And if we look at these validation steps, there's a couple different types of validations that are occurring. There's this first validation, which is looking at is the chunk size of the current chunk that's being unlinked equal to the previous size of the next chunk. Now, this has nothing to do with bins and lists and the pointers. This is about the next chunk in memory, the actual location in memory. And so if we look at this next chunk function, how do we know where the next chunk is in memory? Well, we take the pointer, which is where we're at, and we add our size. So whatever's at the end of the current chunk is the beginning of the next chunk, because that's how the heap is defined. And so that is the next chunk. And the next chunk better have a previous size that matches what I claim my size is. And so this is about locality in memory. This second check, this validation step, this is about the doubly linked list. It's does the back pointer of my forward pointer equal me? And does the forward pointer of my back pointer equal me? I know that sounds like something that you wouldn't be able to satisfy or to pass this validation step. But what is it really asking for? It's asking for a pointer where a specific offset is the address of the chunk. And then another pointer where the address at a specific offset is the address of the chunk. Now, these pointers, forward and back, if we have control over them, these don't necessarily have to point to valid chunks. They just have to point to somewhere where the offset is the address of the chunk I'm trying to unlink. And it is possible to satisfy that constraint. Again, these are about locality. So when we say next chunk or previous chunk, we're talking about where in memory. When we're talking about forward and backward pointers, we're talking about the list of the bins. So we said that we can find the next physical chunk by taking the address of the current chunk and adding the chunk size. Well, can we find the previous chunk? Well, the previous chunk is defined as the beginning of the current chunk minus the previous size. But remember, the previous size is only valid if the previous chunk is not in use, if it's currently free. And how do we know if the previous chunk is currently free? It is in the least significant bits of the current size, of the current chunk size. Now, we saw in earlier modules that if you have an overflow, you can overwrite that size value. We did this to create some overlapping allocations with tcache chunks. So there are scenarios where you can overwrite the size of a chunk that is in front of a chunk that you have write access to if you have some type of overflow. And if I can overwrite the size, I have already written past the previous size. So in an overflow scenario, it is possible to set or clear the previous in use and set or clear the previous size. And since the previous size determines where the previous chunk is, there's two different ways to kind of manipulate the heap. You can manipulate it in physical space right here by messing with size and previous size. And that's going to mess up where chunks begin and where chunks end. You can also mess up the heap with pointers based on these forward and back pointers and manipulating them such that a chunk is created from an address that is defined by these pointers. Not specifically from the unlinked chunk function, FYI, but in principle, by manipulating the forward and back pointers, you can also create a chunk. And so there's two different avenues to kind of attack the heap and get the heap to misbehave in a manner that's beneficial to you. And so that is all stuff to think about. But what are the actual exploits? Exploits can be found at this website, github.com/self-shellfish/how-to-heap. This is probably the best single resource I can point you to. I mentioned at the beginning of this lecture that heap exploits are heavily dependent on libc versions. And so when people do write-ups and post them online, it's very easy to come across outdated or incorrect information. This repository is a regularly updated list of heap exploitation techniques that are organized, sorted, and verified by libc versions. These exploitation techniques are written in C with working examples of the proof of concept. They print out kind of what the idea is between the mallocs and the overwrites or overflows or what is going on to try and explain the primitives that are at work. So you can run them and see it in action, that it does work on your system or on your libc. It also has a button where you can run an interactive web terminal. So if you do not have a Linux box to do heap exploitation and playing around with these, you can run a lot of them on an interactive web shell. On the topic of just generally learning about heap exploitation, one of the problems that you run into is you want to see how exploits work on other versions of libc. This repository here, glibc all-in-one, provides a pretty handy tool that you can just say, download libc version 2.32, and it will go out and fetch it for you, build it, compile it, and make sure that it's good to go. So if you are interested in heap exploitation, you'll definitely want to have more than one version of libc handy, and this is a great tool to retrieve them. So in conclusion here, the heap exploits that we're going to be working with will be found in Shellfish How to Heap. And this is the repository. And so we see there is a list of exploitation techniques. There's a description of them. What is the latest libc version? Was it patched? Are there examples of CTF challenges that use this exploit? But for this class, we're going to be on libc version 2.35. So these are the exploitation techniques that work on libc 2.35. There's a number of them, and they all require some type of primitive. And so if we were to open one and take a look, the example code may assume that you have, for instance, a double free, or it may assume you have a buffer overflow. It may assume that you have a use after free, that a chunk gets freed and you can still write to it to modify the metadata. And so you need to be thinking about what primitives do these exploits require, and then what primitives does this exploit grant me? Because what these techniques do is they take something that you have, like overlapping allocations, and turns it into an arbitrary read or an arbitrary write. And so heap exploitation becomes about turning primitives into other primitives until you ultimately accomplish what it is that you need. So to be successful in this module, you will need to pay attention to this repository right here, because that is going to be your best resource for understanding what you can do with heap exploitation.